Hello, everybody. Welcome to MOS Live, where in just a moment, several of my colleagues are going to try to answer any questions you have about the huge topic of Earth science. If you're joining us from home and would like to ask questions, you can simply do that in the Q&A section of the chat. And if you're joining us on either Facebook Live or YouTube, we're so grateful you're joining us today, but unfortunately, we're unable to see questions through those mediums. My name is Matt. I'll be your moderator, but at this point, I'm going to invite my colleagues to show themselves. I will disappear for a while, except as a disembodied voice, and my colleagues will tell you their favorite thing about the topic of Earth science.
Hi everyone, my name is Becca. My pronouns are she and her, and my favorite part of Earth science is anything geology related. So I really love talking about rocks and minerals and volcanoes, as you can probably tell from my background behind me.
My name is Chuck. I use he, him, his pronouns, and I like the way that all of the Earth systems interrelate with each other and that they're all interconnected. If a change happens, a major change happens in one system, it affects all of the other systems. So I really like talking about all of the Earth sciences, not just geology, but weather, the oceans a little bit, and how they all relate to each other.
My name is Meg. My pronouns are she and hers. And what I love the Earth. The Earth is such an amazing place. It's a really unique planet. And I really like how much you can understand about all of the different systems on Earth, about plate tectonics, about the atmosphere, just from some like very straightforward, all the laws of physics. So I kind of approach it that way, like how much you can learn just from knowing how the sun shines on Earth, how it rotates, how the tectonic plates move and how oceans open and close, and what we can take from all that knowledge and also learn about other places in the solar system as a result.
Thank you so much. Now, we're a little slow getting started with questions, so I thought to warm up our friends at home, we could start with kind of a round robin. Could each of you pick something about geology that has had an effect on New England and how it's shaped? And you can pick something different, maybe give an example of a landform or something in New England that was created by some sort of geologic process.
I could start. Oh, sorry. Well, I'm just gonna, this is coming from a memory that is now like a decade old from when I was a student and I went on a field trip outside in Western Mass somewhere, where we found these really neat features called potholes, which are remnants, they're features that are left behind by retreating glaciers. This whole area once was covered by a big wall of ice, and once those glaciers melted and retreated away, they left all sorts of these like neat New England landforms all around. And these potholes are sort of these, it's not the kind that you see in the road. They're like these really neat dips in the rock, just carved into the rock, where there are all these like eddies and ice scraping boulders around each other and making these really cool round hollows everywhere. So I've always kept that memory with me, and it's only one of like lots and lots of cool glacial features, but it's one that's a really fun one. So there you go.
If you especially go to Western Massachusetts or up into Northern New England, you will notice there are lots of mountains. We have the coastal plain here in Boston where the land is relatively flat with some hills, but mountains, the landforms get much more exaggerated. You get more higher mountains if you go up to Vermont, New Hampshire, Maine, and so forth. Why is that? Well, it turns out that the mountains in New England are just part of a larger chain that extends all the way from Quebec down to the steep south into Alabama and especially Georgia. It's called the Appalachian Mountains. And the Appalachian Mountains are one of a number of mountain ranges that has existed along the eastern seaboard of the United States. And this has to do with something called plate tectonics, in that different parts of the earth were in different positions in different parts, in different times of the past. If you go back in time about 200 million years or so, the continents were all joined together, and Eastern North America was butted right up against the African and European plates. So you could, so those continents, these continents were mushed together in a supercontinent. And when that happens, you tend to get mountain ranges along the boundaries where they were mushed together. The continents have since drifted apart, but we have the mountains that were resulted when older continents collided and made that big continent, and then they pulled together apart, and we're left with the mountains. 300 million, 200 million years ago, the mountains of northern New England were much higher than they are today, but they have been eroded down. Weather and other factors that happen on the earth, because the earth is a dynamic place, mountains are always being eroded down and worn down. So the highest point is only about 6,000 feet. It may have been over double that several hundred million years ago.
And my favorite part about Massachusetts and New England geology, but specifically Massachusetts, is not really a feature, although there are some really cool ones, but it's more kind of like a fun fact. Here in Massachusetts, we have almost every type of rock there is. We have a lot of different types of igneous rock, which come from volcanoes. We have a lot of types of sedimentary rock, which come when different pieces of sediment or small pieces of rock settle over time. And we have different types of metamorphic rock, which have been changed by temperature or pressure. Here in Massachusetts, we're pretty unique because we have so many different types of rock, and our geology is very diverse.
Awesome. Well, we got our first questions from friends outside, from Sylvie and Poppy, who are 10 at 7. And you started to introduce this a little bit, Becca, but maybe we could expand on it. They want to know, how did rocks form? And if I could add a little extra to that, maybe talking about just what exactly is a rock and what isn't a rock.
Sure. So I can definitely jump in on that. Kind of first thinking of what is a rock and what isn't a rock, that's a really good question, because there's a lot of things out there that don't make up rocks that maybe we think are. A rock is, well, it has to have 2 or more minerals that make it up. If it just is one mineral, like quartz, if you were to find that, that's not really a rock. It is just a mineral if it's just one. But if you have 2 or more, you make up a rock. And so really anything that has 2 or more minerals would be classified as a rock. And when we're thinking of how they're made, well, as I said, there's 3 different types. And so some rocks are created when a volcano erupts and that lava cools and it becomes a rock. So a lot of the igneous rock that I was talking about has all come from a volcano, either outside or inside, and it eventually turns into rock when it solidifies. It's no longer molten magma. But when you have 2 different other types, the metamorphic and the sedimentary, generally those come from different types of rocks. You could get an igneous rock that turns into metamorphic when it's changed by temperature or pressure. Or you could also have one that sort of breaks down over time and turns into sedimentary. So there's actually a lot of different ways that rocks can be created. And there's even such a thing as the rock cycle, where it could start out as one type of rock and turn into another type of rock over a long period of time, depending on the conditions.
Awesome. Okay, so here's one about rivers. And I can personally attest to some curiosity on this, because I have originally lived in New York City. And of course, our famous river is the Hudson, which is extremely broad and fairly straight, coming all the way from New York State down to the Atlantic Ocean. When I moved here and saw the Charles, I was surprised by the fact that it was so different. It's much narrower and it's so twisty-turny and goes all over Eastern Mass. What is it that makes rivers form in these different ways?
I can take a stab at that, or Chuck if you'd like to. But I grew up along the Hudson River, so I also have a very clear picture of that particular river in my head. But if you look at lots of other rivers, including the Charles, but for example, the Mississippi River or the Missouri River, that like these huge sprawling meanders that make these really big loops. If you look down from above, you're right, it's very striking. And sometimes even those meanders can sort of cut themselves off as the water's redirected and leave sort of stranded branches here and there. So if you look very closely, you can see sort of the old path of the river in addition to the current path. And it makes for a really interesting and dynamic topography. So you can really, really see how the landscape changes, even something as permanent seeming as a river. And the reason why that's happening has to do with the way that the water is flowing along a path that is not straight. So Chuck just mentioned earlier about how the mountains get weathered down over time. That weathering process is also something that is happening in rivers as they flow along, because water actually has lots and lots of force to it. And as that water is flowing, it's actually wearing down the material that it's flowing through, even if it's something that's like really, really hard rock. And this is how you get a lot of canyons that are cut over time, because you have enough time. This very, very, very slow erosion process of the river is actually creating that topography. And the thing is, as the water is flowing around a curve, it's not cutting away at the same rate or as much in different parts of the curve. So it's actually a little bit faster. It's cutting a little bit more on the far end of the curve, and it's actually cutting less or even depositing material along the inner part of the curve, which means that you're making the curve wider and wider as it goes on. And then eventually, like I mentioned earlier, out of order, as it's making that curve like wider and wider, eventually the river will adjust. Something will happen. The topography will level out to an extent where it finds there's an easier path to just go over the loop and skip that whole bend or meander to begin with. And then you get these abandoned meanders. And the whole river system can just evolve like that over time. So.
Very
Particularly the Mississippi River is a great example of that. There are these meanders that have been abandoned where the river has just bent so far from a straight path that it actually cuts through the meander that it has just made and leaves water abandoned. There's a lake that results from that, which is kind of the trapped water that's left behind the old meander, called an oxbow lake. And those are very common in the Mississippi Delta, or in the lower part of the Mississippi Valley. Not so much around here. And so I just think it's amazing how the river is, what happens to a river is not just affected by the water that flows down, the sediment that it is carrying, but also the different hardnesses of the rock that it's passing through, and also how arid the climate is. You tend to go canyons more out in the west because of the different way that rain interacts with the different kinds of soil that are there. There's a lot of sandstone out there. Rain can be infrequent and quite violent, and that results in a different kind of configuration to the river channels. And you tend to get a lot of canyons out there because there isn't a lot of the soft top soil we get here. There aren't a lot of the trees out west that we get here, which tend to mitigate and alter and kind of modify the flow of the rivers. So rivers will have a different character in arid regions which don't get a lot of rain versus other areas which do get a lot of rain, like here in New England, with the exception of this summer so far.
nice. All right, Poppy and Sylvia have hit us with another one. They want to know how volcanoes form, and maybe we could add a bit to that, by the way, which is, do we ever get volcanoes here in Massachusetts?
Yeah, that's a great question. So volcanoes actually form in a number of different ways. Most of the time, they form along plate boundaries. Now, the Earth is broken up into different tectonic plates that move in different ways and sort of push against each other or pull against each other in a few different ways, especially depending on which type of plate they are. And most often, volcanoes form at these boundaries. So there's ways when plates start pulling apart and it kind of has magma come up, and that's a divergent boundary where they're pulling apart. And that is what we actually see in the middle of the Atlantic. The mid-ocean ridge has a big long chain of volcanoes down it, and they are from that process. But then there's also ones called subduction, where two plates collide together, usually an oceanic plate and a continental plate, which is a lot thicker. And the oceanic plate goes underneath the continental plate. And as it's going under, it melts some of the rock and some other fluid gets in there, and it forms little volcanoes that pop up along the continental plate. That's kind of like the Ring of Fire. So all of South America along the Pacific has a lot of volcanoes because of that. And the third main way that volcanoes are formed from is when there's something called a hot spot. But basically what it is it's just this big amount of magma coming up from the mantle underneath the crust of the Earth, and usually going through oceanic crust to create volcanoes like the Hawaiian volcanoes. But occasionally it goes underneath continental crust, which is much, much, much thicker, and creates a much larger volcano. And that's how you get Yellowstone volcano, which is also my favorite volcano to talk about. But as far as Massachusetts goes, we have absolutely 0 active volcanoes, but we do have extinct volcanoes in the area. And so it's really interesting to notice that at one point this was a volcanically active area. However, it will not be again, unless things change drastically, but that will take millions and millions and millions of years.
Excellent. Okay, we've got a question from Betsy. I'm going to infer a little bit from it. She asked, why do we have Earth? What I'm thinking she's interested in is, why do we have the Earth the way it is compared to 2 other planets in our solar system, like Mars and Venus? Earth is so different, and obviously it's capable of life. What exactly happened on Earth to make it that way that's different from Venus and Mars? And in less than 5 minutes.
Well, we have any star that has planets around it, and we're finding many, many planets going around stars. We'll have a region around the star where a planet, if it's in that region, is the right distance away from the star for water to exist as a liquid on that planet for long periods of time. Why is that important? Well, what's the major difference between Earth and the other planets is that Earth is the only planet known to have life on it. And life as we know it requires liquid water. Now, life likes that best. And the Earth just happened to form at the right distance away from the sun with the right kind of chemistry and the right kind of history for liquid water to be present for hundreds of millions, if not billions, of years on its surface. That was not the case with the 2 neighboring planets that Matt was talking about, Venus and Mars. Venus is too close to the sun for water to exist as a liquid, but there are a lot of other just as important factors in the history of Venus. Unlike the Earth, Venus does not have a magnetic field, and we have found that magnetic fields are important for protecting the surface of the planet from dangerous radiation from space, including the sun. The sun, in addition to the light and heat that it puts out, emits dangerous radiation, and there is nothing in Venus or in the case of Mars to prevent that radiation from just slamming into the planet and sterilizing it, basically making it not possible for liquid water to exist and making it not possible for life to take hold. In the case of Mars, Mars is smaller. It cooled off faster, and that's significant as well. The Earth has had active volcanoes for all of its history on it, and it turns out that that is important for giving life the toehold that it needs. And as a matter of fact, a lot of the water comes from other parts of the solar system, but some of the chemistry, some of the things that life needs comes from volcanoes. Those are still active on Venus. They're on the Earth. They're active on Venus as well, but because of the other things that happen, Venus is a temperature of 900 degrees. But Mars ran out of its volcanic juice because it cooled off faster. It has no active volcanism. It could not maintain, as a result, Mars cannot maintain the atmosphere, cannot maintain the water balance, cannot maintain the other chemistry that are needed for life. So Earth just happened to be in the right place at the right time with the right kind of chemistry. The other 2 neighboring planets didn't.
Awesome. Now, I think we've struck a chord with this whole volcanoes thing. Emily wants to know if there's any extinct volcanoes in Massachusetts, maybe that she can go and see up close. Is there any evidence of that left?
It's a great question. And sadly, not that much evidence, because a lot of them were basically here since Massachusetts was created. And Massachusetts is a little unusual, like I was talking about, because a lot of stuff kind of just pushed together from the ocean, from the Atlantic, to create it kind of accordion style. And so a lot of it did get ruined in the process. Now, Boston and some of the surrounding areas is basically a volcanic basin. but it's not really easy to see because it's under a lot of topsoil and a lot of other material. It would be pretty difficult to find the actual volcanic material. However, there is a lot of igneous granite throughout a lot of Massachusetts that you can go see, even if you don't know exactly what volcano it's from, or if it's not even from a volcano very recently. Perhaps it's a glacial boulder that has been deposited. Any granite that you find outside came from a volcano. So it is definitely evidence that there was some sort of volcanic activity at some point somewhere nearby. But unfortunately, we don't have any specific mountains that we can point to and say that that was an extinct volcano right now.
Cool. I got one more from Sylvia and Poppy about magma. What is it that forms magma? How come the rock that's so solid on the surface of the earth becomes a liquid if you go down a little ways? What's going on with that?
Temperature.
I'll take a stab. Well, oh, sorry. I was going to say there's a couple different things, and I want to describe my favorite version of why we have magma, but there's other processes. So like, please jump in to fully answer the question. But my favorite process that results in magma is what Becca was talking about in the middle of the ocean at those mid-Atlantic ridges. Those are places where two tectonic plates are pulling apart. And as that happens, the mantle material down from below is actually welling upward. And only because it's moving upward closer to the surface and the pressure above it is going down because there's less rock on top of it, because of that lowered pressure, it actually melts and becomes magma right there at the mid-Atlantic ridge. And that is forming new crust at these divergent boundaries. So the plates are pulling apart. The mantle material, which is solid, is getting closer to the surface. And as it gets closer, it starts to melt because it has less pressure from overhead. And that is where we get lots and lots of our new crust forming on Earth. And there are a few other places besides mid-ocean ridges where you also get this divergent plate boundaries. But for the most part, they're happening deep under the ocean, where the crust happens to be particularly thin as well. But that's only one way that you can get magma, and it's the way where you take off the pressure. Like Chuck was about to say, you can also get there by raising the temperature.
And this interior of the earth is very hot, much hotter than the solid crust. And so all you have to do in the oceanic crust is go down 5, 10, 15 kilometers and you're into 2,000-degree rock. Now, it's not just that simple that you have the cold surface and then the hot rock underneath it. That material underneath in the mantle is moving. And if you think of heating a pot of soup on a stove, what you get when you start to get the soup hot is you get these rising and falling currents. And you get it's called convection, and that's what happens when the soup being heated from below is rising, and then it cools, and then it falls. The same kind of thing is happening with the rock in the mantle, and with the hot spots that Becca was talking about in several places on the Earth, most often under the ocean, but also occasionally throughout the Earth's history under the crust, you get these rising mantle plumes, they're called, where the hot rock is just welling up. And that has the effect of first moving up the oceanic crust and then breaking through it and accumulating on the ocean floor. So the Hawaiian Islands, as a result, have been building up and up and up over hundreds of thousands, or if not millions of years, until they break the surface and form this island chain. Now, the ocean surface, the ocean bottom floor is moving with respect to this hot spot. So as the convection comes up and breaks to the surface, the ocean crust moves over it. It basically bores a series of holes or makes some mounds of lava that come up. That's why we have a chain of islands. The farther northwest you go in the Hawaiian chain, the older the islands are, more eroded they are. The most intense activity where that mantle plume is coming up now is at the southeastern part of the chain, the big island of Hawaii, and another island, which in a million years or so is going to break the surface, is a new island called Loihi. So there's a lot going on underneath the surface that causes this magma to come up.
Awesome. And actually, just to finish the whole volcanoes thing, Becca, maybe you can answer Betsy's question about why exactly is it that when lava hits water, it becomes hard? What's going on there?
Yeah, that's a great question. It's kind of the same thing that happens when lava hits air. Basically, the water or the air, depending on wherever it's coming out, is so much cooler than the actual magma. Once it comes out, it becomes lava. But this molten rock is incredibly hot. It's hundreds of degrees Fahrenheit. And when it hits, say, water, which might be 50 degrees Fahrenheit, that is such a difference in temperature that it almost instantly cools. Now, there are some times where that lava might be coming out a little bit more eruptively, in which case maybe the outside of it will cool, but the inside may flow a little bit more, kind of creating a little bit of a shell, or what we call lava tubes, really. But most of the time, it's going to cool the entire thing down pretty much immediately because of that difference in temperature.
Awesome. And we are just about out of time. So I thought we would end with something I always think is kind of cool, which is giving people a chance to discover things for their own. I would love it if each of you could recommend some place in New England that is just awesome geologically for some reason, someplace that if people want to see a cool example of earth science, they should put it on their list to visit. Do you have any suggestions?
Mount Washington is my suggestion. On the eastern side of Mount Washington are two basically scooped out hollows called Tuckerman's Ravine and Huntington Ravine that are a result of glaciers. And glaciers are part of earth science as well. They have to do with the weather, they have to do with the climate, and they have to do with the fact that ice over time will wear and grind down rock. So what happened hundreds of thousands of years ago, tens of thousands of years ago, is that all of New England was overlaid by this massive sheet of ice. And ice, because snow fell, didn't melt the previous summer because it was cold. More snow fell on top of that, more snow fell on top of that. And so you have this thick layer of ice, which has weight. And when it starts to slide downhill, it has power to grind away the rock. So if you look at Tuckerman's Ravine on the east side of Mount Washington, you will see a place where this accumulated ice, the weight of it is just scooped out this hollow in solid rock. The solid rock of Mount Washington over the course of thousands of years.
And this is a little bit of a different branch of geology than we have been talking about, but it is National Fossil Day, so I would be pretty remiss to not actually say anything about this. But in Holyoke, Massachusetts, there's Dinosaur Footprints Park, and you can actually go and look at fossilized tracks of dinosaurs in Massachusetts, which I just think is super cool because that merges both of my favorite topics, dinosaurs and rocks.
Mm-hmm. Yeah, and I'm just going to double down on glacial features and go back to what I said at the very beginning, the potholes that you can find, which I'm just going to share a quick picture if I can. Oh, no, I can't. Okay, never mind. Never mind. But I did look up where they are coming from or where it was that I went. And it's Shelburne Falls, Massachusetts. If you have a chance to go out there and play on the rocks there, you can see the really cool swoopy shapes that the glaciers left behind.
That's so awesome. I've been to two of those places. In fact, I went up Tuckerman just a few weeks ago, but I've not seen the potholes. I'm looking forward to adding that to my list. And at this point, we are out of time, so I apologize if there was any questions we didn't get to. I'm going to ask my colleagues to please say goodbye and then to turn off their cameras.
Bye, everyone.
Bye, thank you.
And speaking for myself and for the rest of the Museum of Science, we're so grateful to all of you for joining us today on our program. We just want to remind you that we'll have a program every single day, and we hope you'll come back and check this out often. And if you'd like to support the museum, you can do that by coming to engage.mos.org/welcome. Thank you again for joining us at MOS Live.